Hey guys, in this video we're doing a quick review of what we learned so far in AP Physics 2. So the first thing we need to review is the letter for proton. So the letter for proton is P, and the letter for neutron is N, and the letter for electron is E. And the mass of the proton is 1.673 times 10 to the negative 27th power kilogram. Neutron's mass is very close to protons, and electron's mass is very close to it's not close. It's relatively smaller, and very small compared to the mass of the proton and neutron. And the ratio of MP divided by ME is about 1:836 divided by 1. You can see the ratio is quite large. And the second thing we need to review is the conservation of charge statement, which stated that in a closed system, the closed system is defined by, or it means that the particle does not leave or enter a system. So in this system, like here's negative, positive, the negative or positive cannot go out, or the electron or negative charge particle cannot go into the system. So for the closed system, all the particles cannot leave or enter the system. And in a closed system, the total amount of charge is conserved. So in a closed system, like the total charge, for example, like +8, like if the system is closed, it cannot become charge 9 in some points, okay? Or become +7. It cannot, because of the conservation of charge statement. Okay, the next topic we're going to review is polarization. So polarization occurs when an electric field distorts the negative clouds of electrons around the positive atomic nuclei in a direction opposite the field. And this slight separation of charge make one side of the atom somewhat positive and the opposite side somewhat negative. So for conductor metals, because we didn't learn about electric field, I'll just erase it for more clarity. So if you put a large negative charge over here, the large negative electron will just repel the negative electrons over here. So that way, or in this case, like if you put a negative charged particle over here, it will just repel the negative charge particles, and the positive charge will be just attracted to the negative charge particle. So this will result in stretching. Like initially, if you don't put any charge over here, it will just remain in this state. But when you put a negative charge particle over here, it will repel the negative electrons and attract to the positive ions. So thus, it will look like a spring stretching. And that is how polarization works. And for conductors, it is like metals. So when you put a negative charge electron over here, the electron inside the metal are free to move. It is not like the insulators. So you can visualize the electrons as like sea or liquid. So when you put negative charge particle over here, the electrons inside the metal will just float out and will just go that direction. So that's why the conductors can conduct electricity. Okay, we're going to review about semiconductors, which are like silicon or germanium. So for the semiconductors, when the temperature is low, it will behave like insulator, and when the temperature is high, it will behave like conductors. So when the temperature is low, like the positive and negative, this one is electron and this one is ion, will just like attached by a string. Like it is not exactly a string, but you can visualize the attraction as a string. Okay, but when the temperature is high, that spring will just break. So now the positive and negative are separated, and the negative charge electron can just move like the water, which is similar to the metals. And now we're going to do the structure of atom. So atom has different like energy levels. So for the first energy level, you can put 2 electrons over here. And the maximum number that you can put in the first shell is 2e, and for the second shell is 8 electrons, and for the 18th shell, or the third shell is 18 electrons. And how do you calculate the charge of an atom? Okay, for example, like if it is charge 8, and here are this. So the total charge is equal to the sum of positive charge minus the total number, or the sum of negative charges. And in this case, we can see the number of positive charges is 8. So 8 minus 1, 2, 3, 4, 5. 5 negative charge particles. So 8 minus 5 is 3. 3e. And you need to add an absolute value. Now let me erase this stuff. And now we're going to review the magnetic field. So for the magnitude of the magnetic field of a current or the magnetic field around a wire is equal to mu I divided by 2 pi r, where r is a distance from the wire to the point, or A. And mu is a constant, and I is the current. And the direction of the magnetic field, you can just use the right-hand rule. Which stated that if you, the direction of the current is your thumb, and you use 4 fingers, and which is bend towards a wire, and the direction of the fingers is the direction of the magnetic field. So this, let me try it. This is the direction of the magnetic field. And for a looped wire, at the center, you need to remember that the magnetic field is equal to mu I divided by 2r, where r is a radius. And now for the magnetic force, it is equal to I, the current, and times L, where L is the direction of, or the length of the wire. And there's a direction to indicate the direction of the current. And B is a magnetic field. And from cross product, we know that the magnitude of the cross product is equal to ILB sine, where sine is an angle between like the L and B. This is the angle. And for the direction, you need to use the right-hand rule, version 2, which is that the palm is in the direction of the first vector, and you use your fingers to fold to the direction of the second vector, and the direction of the sum is the direction of the resulting vector. What I mean by is that this is the direction of your palm, and you use your fingers and fold it to the direction of the magnetic field, and you can see that the sum is just going down. So this is the direction of the resulting force. And for the second equation, which is F equals qvb, where v is a velocity of the particle, and b is a magnetic field. And for this case, it is important to know that q can be positive or negative. When it is an electron, it is negative, and when it is a positive ion, it is positive. So, for a positive ion moving that way, and the direction of the B is going into the page, using the right-hand rule, use your palm first, and fingers fold into the page, and you can see the force is acting up. And for the negative charge electron, use your palm and fold it to the direction of the magnetic field, and you can see V cross B is heading up, but it is important to note here that Q is less than 0. So it will be the negative direction of the of B cross B. So the force will go down instead of going up because it is negative charge, while this one is positive charge. And moving on, we're going to talk about charging by induction. So for charging by induction, you first put a charged particle over here. And now for the electrons inside the metal, you know that the electrons within the metal it's free to move. So when you put the negative charge particle over here, it will just repel the negative charge electrons. And this will result this side to become positive and this side to be negative. And when you connect the metal to the ground, the electrons are now free to move, okay? It can be repelled further and goes down to the ground. But, and now, the overall charge of the metal is not positive because negative electrons move away to the ground. And when you remove the electrons, now the charge will be left alone, and this will result in like the charge to spread evenly on the surface of the metal. And we're going to take a look at charging by friction. So for charging by friction, you just need to know which object is more electron, which object likes the electron more. So in this case, when you rub a rod and the fur, and you see that the rod becomes negative charged, That means the rod likes the electron more than the rubber. Oh, well, than the fur. So the answer choice over here is C, which stated that the molecules in the rubber rod have a stronger attraction for electrons than the molecules in the fur. And moving on, we're going to take a look at how will charges distribute in first metal and the second in insulator. So for the metals, the charges will distribute evenly if the object is a sphere. And there will be no electrons or charged particles inside the shell. Like there's no charged particles over here, or here. It is on the outer surface. And for the insulators, the charges will just spread evenly because, like, for this model, it is not free to move, okay? The electrons are not free to move, so it will stay in place, regardless if you apply an electric force to the insulator. And now we're going to take a look at the Coulomb's law, which stated that electric force equal to K times Q1, Q2 divided by R squared, where R squared is a distance between the two charged objects, and K is a constant, which is equal to 9.0 times 10 to the 9th power of times Newton times meter squared divided by Coulomb squared. And K can also be written as 4 pi epsilon 0. You can know that, or you can ignore this fact. And now we're going to take a look at circuit. And for the like resistor connected in a series, the equivalent resistance is equal to R1 plus R2 plus R3. And when the current passes through each resistor, the electric pressure will just drop. And for the parallel circuit, the R equivalent is equal to 1 divided R equivalent is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. And the voltmeter measures the voltage of or the electric pressure on the sides it connects. So for this case, if you put a voltmeter over here, it will measure the pressure difference between this point and this point. And if you just connect the voltmeter like this, it will just measure the pressure difference between the red and the blue part. And for ammeter, it measures the current that is passing through it. So if you put an ammeter over here, it will just measure the current that's going through the series. And we put an ammeter over here, it will just measure the current that is going this way. When we put it here, it will just measure the total current of this system. Okay, now we're going to take a look at problems. So for the first problem, we want to find the charge of the object. And for the charge, it is both Q. And the theta is given, L is given, and M is given, and G is given. And we don't know about T. So to be more convenient, using the force diagram, or because we know that the force is added up to 0. So if you draw a vector diagram, you can see this is mg, and this is kq squared divided by r squared, and this is r. And for r, we know that this side is just going to be L times sine theta. And so now r is going to be equal to 2L sine theta. And now for the force, we know that tangent theta is equal to this side divided by this side, which is equal to kq squared divided by r squared divided by mg. And now if you move mg to that side and r to that side, you can get the equation is tangent theta times mg times r squared is equal to kq squared Fu divided by k to that side. And take the square root both sides. And now you can find the charge of the particle, which q is equal to tangent mg times r squared by k, and where r is equal to 2L by sine divided by sine. And plug in the numbers, you can get q is equal to tangent mg times 4L squared times sine squared theta divided by k. Okay, moving on to the second question, which I find to be kind of interesting. So for the first plus q, we know that the electric force is equal to F is equal to, okay, wait a second. Because you guys didn't learn about E, so let me erase it and change it to F is approximate to KQ big Q divided by X cubed. And for the point of P, there's a particle with charge Q. And now we know that distance is equal to d divided by 2. Now using the Pythagorean theorem, we know this side is just going to be d divided by 2 squared plus x squared. And we just draw a force diagram over here. This is going that side, and this is going by to that side. And by symmetry, we can see that we'll just result in another vector that is just perpendicular to this line, because it is symmetrical. And now we just need to care about the force that is acting in this direction. And for this force, we know the magnitude is equal to k small q big Q divided by r squared, which is equal to k small q big Q times this. And we want to separate the f into the direction that is perpendicular to the line and the direction that is parallel to the line. So for this, we know that this is f, and this is just going to be f sine theta. And similarly, this is also the case. Let me draw a diagram right here. So this is theta, and this is also kq squared. Oh wait, k small q big Q times d divided by 2 plus x squared. And now, if you add up the force in this direction, it is equal to 2 k small q big Q d squared plus x squared, and there's a sign. And for the sine theta, it is equal to this side divided by this side, which is equal to d divided by 2 times this. And when x is very, very large. You can just ignore this term because this term is relatively smaller than x. So this term will just approximate to x squared, and this term just approximate to this. And now just divide the two, and you can get the resulting force to be k small q big Q times x cubed, which is consistent with the answer over here. And moving on to question 3. So in this case, I will change the question a little bit. So in this question, we know R and Y, and we want to find V. Okay. So for the Coulomb's law, from Coulomb's law, we know the attraction force equal to K, because the charge of the proton and the electron, we assume it to be the same, or it is the same. So K E squared divided by R squared. And this will support the centripetal force, which is equal to N V squared divided by R. And now, if you just move R to that side and M to that side, and you can get V squared is equal to K E squared times or divided by MR. And now, just take the square root to both sides, and you can have V is equal to square root of K E squared divided by MR. And you're done with this problem. And move on to question 4. In this question, we know the Q and the V and B, and we want to find the distance of this. So when the positive charged particle enters the region 2, which is filled with B, so we'll just deflect. We'll deflect, and we'll eventually hit here. So we know that from QV cross B, this is a magnetic force. Because it is the velocity and the B is perpendicular, sine theta is equal to 1, and this is going to be equal to QVB. And we'll also support as a centripetal force, which is equal to V squared divided by R, where R is the radius of the circle. And now, just move R to that side and move this stuff to that side. You can have R is equal to mv squared divided by qvb, which is equal to mvbq. And you know that the d is equal to 2r, where this side is 1r and this side is 1r. And now you can see that d is equal to 2 mv divided by bq. Okay, we're going to do the fifth question. So the fifth question is about what is the force per unit length on wire 1? Wire 1. So for wire 2, we can use the equation above. Let me see. So this equation over here. And also this equation over here. The first equation is B is equal to mu 0 I 2 divided by 2 pi R2. And the second equation is F equal to I1 L1 B2. So by using the right hand rule, we can see it just circulate around the current. And this is the direction of the sum, and use your forefingers to fold around it. You can see that the direction is that way. And this B is perpendicular to the direction of the current. And now you can see that F is equal to I1 L1 B2, and I cross B, where L is the direction or the length and the direction of the current. And using the version 2 of right-hand rule, you can find the direction to be, let me see, to be that way. Okay, that is correct. And we know that R1 is equal to 12 centimeters, and I2 is equal to 2.0 amp. So the magnitude of the B produced by I2 is equal to this. And location of the I1, it will feel a force of IL1B2. And for force per unit length, you just need to move I1 to here. And now you can get the equation to be F1 divided by L1 is equal to mu 0 I2 divided 2 pi R2 times I1. Okay, we're done with this question. And moving on to the sixth question, which is, what is the equivalent resistance of the arrangement shown in figure over here? So we need to find the electric pressure. We just need to label the electric pressure over here first. So we'll just go that way and that way. And now just color it. Just go to here. That is green over here. And wait, let me change color. And you can see this three is in parallel, and these two are in parallel. And now you can draw the circuit in this form, which should be clear. Okay, so here is 4, and here is 10, and here's 8, and here's 4, and here's 5, 6, 3, 2. And for this stuff, let me just highlight it. And for this stuff, the R equivalent is equal to 6 plus 3 plus 2. Okay, let me calculate first. Never mind. 6 plus 2, 6 plus 3, 6. Okay, 2, 3, 5, 1. Okay, this one is equal to 1. So the R equivalent is equal to 1 ohm. And now for this two, we know the equivalent of the yellow part, and we want to find the equivalent for the green part, the total green part. So we just need to add 5. R equal 1 plus 5 is equal to 6 ohm. So the green part is equal to 6 ohm. And for the red part, so the R equivalent is equal to 1 divided by 8 plus 1 divided by 4, and times 2, 2. It is equal to 3 divided by 8, and R equivalent is equal to 8 divided by 3 ohm. And just plus 10. So the total in this area is equal to 10 plus A over 3, which is equal to 38 divided by 3 ohm. And now, for the overall, which is this part, it is equal to the first part, which is equal to 38 divided by 3 ohm. And the second part, which is equal to 6 ohm. So the R equivalent is equal to 38 plus 6 ohm, and you can find the, let me use a calculator. Three divided by 38 plus 1 divided by 6 equal to this, and this one is 0.245614, and 1 divided by 0.245614. So our equivalent is about 4.07. And now, this and the orange part is in series. So the total or the overall equivalent resistance is equal to 4.0 plus 4.07, which is equal to 8.07 ohms. And now move on to question 7, which is to find the total power delivered to the circuit shown in this figure. And similarly, we need to draw the electric pressure over here first. So just connect. And this is the yellow part. And this is the green part. And here's the blue part. And from this, you can draw the graph as, let me draw it first. And these two are in parallel. Oh, they're not in parallel. Let me see. This one is kind of hard. This is the first one and the second one. Okay, here. So this one and this three are in parallel, okay? Which is shown in the graph over here, or diagram over here. And now you continue to draw. You can see these two are in parallel. So the first one, 10, and the second one is 5. Ten, 5, 10, 2, 6, 4, and this one is 12. Okay. And for this part, our equivalent is equal to 1 by 4 plus 1 by 6, and you can find the answer on your own. And you just plus 2, and you can find the total equivalent of this. And here is also a parallel circuit, so you can find this. And you just plus 10 over here. And for this equivalent, it is equal to, our equivalent is equal to 1 by 10 plus 1 by 5. And now you just need to add our equivalent. And you can get a number, blah, blah, blah. And the total power is equal to P is equal to I squared R, or is equal to U squared divided by R, or is equal to UI. And in this case, we know the U and R, so we can get this is equal to 24 B divided by R equivalent. And we're done with this problem. Okay, we're doing question 8. So 9 resistors, each of value of R and connected in a ladder fashion. And in this, what is the effective resistance of this network between point A and B? And for this part, it is in series, so it will be equal to 3R. And for this part and this part, they're in parallel, so R equivalent is equal to 1 plus 3. So this will equal to 3 plus 1 ohm. So 3 ohm. So the R equivalent is equal to 3 divided by 4. And now the diagram will just look like this. I'm tired. R equivalent is equal to 4 ohm. And now for this circuit, it is in series, so it will be equal to 3 divided by 4 ohm plus 2 ohm. Oh, wait. Oh my God, what I'm doing. So I assumed R is equal to 1.0 ohm, okay? And now this will equal to 8 plus 3 divided by 4 ohm. So it is equal to 11 divided by 4 ohm. And it is in parallel with this. So the R equivalent is equal to 1 plus 411. It is equal to 4, and this divided by this is equal to 1511. And so the R equivalent equal to 11 divided by 15 ohm. And now if you plus, because this one, and this one is in series, so the total is equal to 2 ohm plus 11 divided by 15 ohm, which is equal to 13 plus 11 divided by 15 ohm, which is equal to 41 divided by 15 ohm. I hope that's correct. And for the last question, we're going to take a look and find the current in the circuit. So here's a motor. It is pulling an object upward at a rate of v. So the velocity is v and the mass we know is m. So the tension in the string is equal to mg. And we know the power is equal to Fv. So in this, P is equal to mgv. And we know that U, and we want to find I. We also know that P is equal to Ui. So in this case, we assume the power is all going into pulling this object. So P are equal to each other. P Ui equal to mgv. So now I is equal to mgv divided by U. Okay, we're done with the lecture.